Hi guys, I want you to take about 5 minutes to look at your answers again from the first two problems here, and then also try to attempt the last two. I'm going to pause and put up the answers to ozone and tin chloride ion, and I want you to pause the video, try to do selenium chloride and carbonate, and then we will come back and you can see the answers. So make sure you pause right now. Great, hopefully you paused. And here are the answers for what we went over last time. So we had 18 valence electrons in ozone. We determined that there were 3 electron domains because of these 3 electron groups. So that's trigonoplanar. 2 of them came from bonds, 1 came from a lone pair, so that gives me trigonoplanar bent, which is less than 120. Over to tin chloride, we have 26 valence electrons. We have 4 electron groups, which is tetrahedral, 3 of bonds, 1 lone pair, so that's trigonopyramidal, and it's less than 109.5, technically 107. So to talk about selenium chloride, I have selenium has 6 electrons, it's under oxygen, plus 2 times 7 from chlorine, so that's 14 plus 6 is 20 electrons. So we'll put a selenium here. Let's do 2 chlorines. We're going to fill in our lone pairs, so I have 2, 4, 6, 8, 10, 12, 14, 16 from the bond, 18, 20. So everybody has an octet that way. I have 4 electron groups, 1, 2, 3, 4, meaning that I have a so 4 electron groups means a tetrahedral electronic geometry. The molecular geometry, so we have 2 bonds, 2 lone pairs, so my molecular geometry is bent. So I'm tetrahedral bent, meaning my bond angle is less than 109.5, just like it was for tin chloride. Great, so now carbonate. I have valence electrons from carbon are 4, plus 3 times oxygen. Oxygen is 6. And then I have a -2, so I need to add 2 electrons on there. So I have 18, 24 valence electrons. So I will do carbon with oxygens around it. 2, 4, 6, 8, 10, 12, 14, 16 on the bond, 18 on the other bond, 20, 22, 24, and I'm done. But the issue is that carbon does not have an octet, so we're going to remove one of them. It doesn't matter which one. In this case, they're equivalent, and put a double bond. Great. Okay, so we have how many electron groups? Hopefully you're saying it out loud to each other. 1, 2, 3. 3 electron groups means we are trigonoplanar for my electron geometry. Now they're all bonds, so 3 bonds on the carbon, 0 lone pairs, right? We're only looking at my central atom. So that means my molecular geometry, I'll just call it Mg, is also trigonoplanar. So my bond angle will be 120 degrees. Great. So now these are the next 4. This was for our expanded octet, so our last 2 electron domains of 5 and 6. So we did sulfur tetrafluoride and iodine pentafluoride in class on Wednesday. So I want you to go review, make sure you've done it, and then go do the next 2, the bottom 2, iodine chloride, tetrachloride, and bromine trifluoride. Pause now and do this. Set a timer for about 5 minutes, and then let's show the solutions. Okay, now that you've paused, waited, and have done the last let's go over these again. So we have sulfur tetrafluoride. We have 34 valence electrons, giving us 1, 2, 3, 4, 5 electron domains, which is trigonal bipyramidal. Since 4 are bonds and 1 are lone pair, that is seesaw. So our bond angles are less than 120 and 90. And then for iodine pentafluoride, 42 valence electrons. So I have 1, 2, 3, 4, 5, 6 electron groups, which is octahedral. Now 5 are bonds and 1 is a lone pair, so that is square pyramidal, meaning that our bonds are less than 90 degrees. So moving on to these next two, I have iodine tetrafluoride. So that's 7 plus 4 times 7, so it's 35, plus 1 from the negative charge, so 36. So we'll have iodine, 1, 2, 3, 4. So we'll do 2, 4, 6, 8 on the bond, 10, 12, 14, 16, 18, that's a bond, single bond, 20, 22, 24, 26, 28, 30, 32. So I need up to 36, so I'm going to do 34, 36. So now we have 1, 2, 3, 4, 5, 6 electron groups, or 6 electron domains. 4 are bonds, 2 are lone pairs. So this electronic geometry is octahedral, and my molecular geometry for 4 and 2 is square planar, meaning my bond angles end up canceling out that repulsion, so making me 90 degrees between the atoms. Okay, last one, bromine trifluoride. I have 7 for bromine for electrons, plus 3 times 7 for fluorine is 28 valence electrons. So I have bromine, and then 3 fluorines. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I need 28, so I'll have 26, 28. So I have my bond, or my electron domains, 1, 2, 3, 4, 5. So 5 electron domains means my, well, and let's just break them down. 3 from bonds, 2 from lone pairs. So my electron geometry is trigonal bipyramidal, but because I have 3 bonds and 2 lone pairs, that means that my molecular geometry, or the shape, is T-shaped. And my bonds are less than 90 degrees on that one, because it squishes them together. Now we're going to talk about how this influences polarity. And before, when we could have a polar bond. So for example, here in carbon dioxide, I have a polar bond. Oxygen is more electronegative, it's pulling in the opposite direction. But because it's linear, so I have another oxygen atom going in the opposite direction with the same amount of pull, then those cancel out. So this is a polar bond, but the whole molecule is nonpolar. So we can see the polar bond here being pulled towards the oxygen, but the whole molecule cancels out and ends up being neutral. So we have to look at the overall shape to determine if a molecule is polar or nonpolar. And then here in water, again, we have the oxygen pulling on the electrons because it's very electronegative, but because we have a lone pair here, it ends up making the shape not symmetric, and so our molecule overall is going to be polar. We can see that we have a red side here, a very electronegative side, that's my partial negative, and then I'm electron deficient on the hydrogen side, partially positive. So here I have an overall dipole, where here my dipole on carbon dioxide cancels out. So the polar bonds leading to a polar molecule due to symmetry. So we'll have those dipoles when our electronegativity difference is greater than 0.4, but we also want to not just consider that, but we want to consider the shape. Now I'm going to tell you a little hint, and I wanted to tell you this in class, so I'm going to tell you it now. You could write this on the side. The general rule of thumb, it's kind of complicated, but just bear with me. So the general rule of thumb, if I have a molecule, let's call it A, B, X, okay, where this is a polar, the bond between A and B is polar. So I have an electronegativity difference greater than 0.4. If I have no lone pairs on my atom or on my molecule, right, on the central atom has no lone pairs on it, so it's completely filled. So I'm thinking linear, my molecular geometry being trigonoplanar, tetrahedral, trigonobipyramidal, or octahedral, so right, no lone pairs, then that molecule will always be nonpolar, always, because all of the dipoles between A and B will cancel out in all the directions. If you have any lone pairs, it will be polar. Almost every time. So most of the time it'll be polar because we're going to have something like with water where the electron pairs shift the molecule in such a way that it doesn't have a dipole, or it has an overall dipole now. It can't cancel itself out. The only caveat to this, if we think about which of the shapes or molecular geometries end up kind of being symmetric, then these are the shapes. So the shapes that end up being kind of symmetric with lone pairs are trigonobipyramidal. So trigonobipyramidal when it's linear. So think I have, let's say A is this, I have B, and I have 3 groups here, 3 lone pairs. Then all of my equatorials are gone. Now I'm just back into a linear shape, and so my dipole will cancel out. The other one is if I have octahedral, so 4 or 6 electron groups. And think about that one. The one where it's all going to cancel out is going to be square planar. So when I have, so I'll write that down, square planar. When I have A, and then I have B, 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 but I have 2 electron groups, and those are coming into the board and out of the board. And so that will end up being very symmetric as well. So that's the caveat. If you see no lone pairs, it's all filled up, then it's nonpolar. If there are any lone pairs, it's polar unless you're trigonobipyramidal linear and octahedral square planar. Another small caveat is if your atoms are not the same. So for example, if I have, let's say my shape is A and I'm linear, I have A and then B and C. So it's linear, right? There's no lone pairs, but the pull between A and C, let's say, might be different than the pull between A and B. And so that type of molecule could be a polar molecule because the dipoles are not going to cancel out in this case. I'm going to have more of a pull to the left than I do to the right. So we want to make sure that our terminal atoms, or these guys on the outside, are the same for these rules to happen. So if it's a perfect world, there's no lone pairs, and your terminal atoms are the same, you're going to be nonpolar. If you have any lone pairs, or you have atoms that are different, terminal atoms that are different, you're polar. And very infrequently will we see trigonobipyramidal and octahedral beyond this chapter. So you don't really have to worry about it too much. Kind of figure it out now, and then you don't really have to hold on to it too much. Okay, so on this one, we're going back to our last practice problems. I know that you're probably flipping back and forth, and please do not try to scramble and write this, you can just go back to your last problems or just look on the board. It's fine, I have it up for you. These were our structures from before. We're going to determine if the molecule is polar or non-polar using our rules. So with ozone, we'll do the first one together, and then I want you to pause and think about the rest and talk about it as a class. For ozone, I have 1, 2, 3 groups, but I have one of them is a lone pair. So based on, even though those atoms are the same, technically, I would be fine if you put nonpolar for this one, because the atoms are the same that they're connected to, all of the atoms. So the dipole, the difference in electronegativity is 0. But because technically there's that electron pair, there is a slight dipole. So this molecule actually, this one you can put polar or nonpolar. I'd be fine for either. But if we go to tin chloride, so here this one's a little bit more straightforward. I have 4 domains. One of them's a lone pair though, so immediately you should say polar. Okay, let's do that for, this should be selenium. Selenium chloride. I have 4 groups, 1, 2, 3, 4. 2 of them are lone pairs, so you should think, I hope you said it, polar. Now carbon dioxide, we have 3 groups, 1, 2, 3. None of them are lone pairs, and all the atoms are the same, so this is nonpolar. Okay, pause, and I want you to do the next ones on your own. Just give yourself like 2 minutes to talk about it. Someone set a timer for 2 minutes, and then press play and continue. Okay, hopefully you paused. I truly hope you paused. Okay, so for this one we have 5 domains, 1, 2, 3, 4, 5. One of them is a lone pair, and this is a seesaw shape. This is not one of our exceptions, so this is polar due to that lone pair. Here for the next one, we have 1, 2, 3, 4, 5, 6 groups. One of them's a lone pair. This is square pyramidal, not square planar, so this also is polar. Now for iodine and trichloride, or tetrachloride, this one has 1, 2, 3, 4, 5, 6 groups. 2 of them are lone pairs, so this is square planar. So this actually would look like this in 3D. It would look like a flat plane. All the atoms are the same, so even with those lone pairs, this is one of the exceptions. This one is nonpolar. And then the last one, we have our T-shaped example. We had 1, 2, 3, 4, 5 groups. 2 of them are lone pairs. This is not an exception, so this is polar. So just to go over it, we have on our board, you can feel free to write this. I already have it written on the board. We'll have kind of the caveat I want to put is, and I'll put a little star, polar if atoms are terminal atoms are different. Okay, so I'm going to put nonpolar with a star. So it's nonpolar, but if the atoms are different, then it will be polar. Here I'll have nonpolar for trigonoplanar unless terminal atoms are different. Same thing with all of these ones where the molecular geometry and the molecular and electronic geometries are the same. Right? No lone pairs on them. They're just bonded to atoms for all of their groups. Okay, the other 2 caveats that are always nonpolar if their terminal atoms are the same are linear with trigonal bipyramidal and square planar with our octahedral. Okay, now for these other ones, so trigonal planar bent is always polar. Tetrahedral trigonal pyramidal is always polar. Tetrahedral bent is always polar. Trigonal pyramidal seesaw is always polar. T-shaped is always polar, and octahedral square pyramidal is always polar. So feel free to write that in. I don't want you to memorize it. I truly want you to understand what's going on. We're really thinking about those electronegativity differences. Next, we're gonna transition into what is hybridization. Now, there's a lot of slides here, but the big takeaway is just connecting our electron domains or our shapes or our electron geometries to hybridization. So I want you to go in with an open mind, try to be positive about it. Don't get yourself in a I'm so confused vibe. Just kind of go along with the ride, and I'll give you the takeaway at the end. Also, when we have molecules that have more than one central atom, so remember, a central atom is connected to more than one thing, more than one other atom. So we want to find those central atoms, and we can do geometry around those. So if I look at this carbon here, it has 4 electron groups, so it has tetrahedral. All of them are atoms, so it's also tetrahedral. Here I have this carbon atom is connected to 1, 2, 3 things, no lone pairs, so trigonoplanar geometry. Now this oxygen has 2 lone pairs here. If we were to do its Lewis structure, it's actually pretty close to this guy actually. It has tetrahedral bent because it has 4, 1, 2, 3, 4 things attached, and 2 are atoms. So that is how we would do that. So I'll let you, if we look at this HCO bond here, it has 1, 2, 3, 4, so it is tetrahedral bent. So its angle is less than 109, or it's 104.5. If I look at this oxygen carbon, then we have this carbon has 1, 2, 3 things on it, so it is trigonoplanar for both, so it is 120.